So hey brilliant minds, welcome back to the channel. This is a physics buddy. In the previous session we started work, energy and power, and this is going to be the fourth session on this. In this session we'll specifically describing what is potential energy, what are the different forms of potential energy, and we'll also try to understand the motion of a satellite around Earth. Apart from this channel has already covered different units from a physics curriculum. Do check them out. Make sure you subscribe to the channel and hit the notification bell to follow the entire series. Stay tuned, let's do this. Yeah. So let's start our today's session. And in today's session, we are primarily talking about potential energy. I gave you the idea about this in the last class, but there are a few more things apart from that which is required to be learned. So I gave you the definition of what potential energy is. So potential energy is basically defined as the work done by conservative force. We also discussed what are the differences between conservative and non-conservative forces. So potential energy is something which is defined as negative of work done by conservative force. So whenever we talk about potential energy, we can simply define it as negative of work done by conservative force. Now, this is the main definition from which we got all the other relations. So we need to keep in mind that whenever we are talking about conservative forces, there are only four types of conservative forces. First is gravitational force, another one is spring force, or you can call elastic force. Then we have electrostatic. So basically, this is a force which acts between different charges. And then we have magnetic force. Apart from these four forces, there is no other such force for which we actually define potential energy. The potential energy can be gravitational potential energy, spring potential energy, electrostatic potential energy, and magnetic potential energy. So only these four forms of potential energy are defined. In our today's session, we are going to talk about these two types of potential energy, as this is primarily the part of this unit. So we'll be defining what is gravitational potential energy, we'll be calculating its expression. Similarly, we'll be also talking about spring potential energy, as well as we'll try to calculate its expression as well. But before actually deriving these equations, I would like to let you know that these equations or expressions are derived using calculus. So without using calculus, you can actually not derive those equations. So I won't give you the derivation part, but yeah, I will definitely let you know that how we actually derive them without giving the calculation thing. So let us start with gravitational potential energy. But before that, we have to recall what was gravitational force. So we talked about this force that suppose if there are two masses and these two masses are separated by a finite distance, let's say d. So the force of attraction which will act between these two masses will be towards each other, and that force with which these two masses attract each other is going to be product of masses divided by square of distance between them. This is what gravitational force comes out to be. So in order to use it to find out what is gravitational force and what is the potential energy, we can simply use this gmm over d square or even r square. So force is important. Without understanding what is force, we cannot calculate work. So let's talk about gravitational potential energy. So whenever we are talking about potential energy, we need to understand this thing that potential means ability to do something. So whenever we're talking about any potential energy, it means ability of the system to do work, sometimes against the force and sometimes with the force. Like for example, suppose this is a planet, and let us assume it as Earth. if there is a mass far away at infinity, we assume. So, how much work the gravitational force exerted from the center of Earth towards the mass so that it got attracted towards Earth. So, what work this force is going to do? That work is going to store in the form of potential energy, or you can say the gravitational potential energy. So, in order to derive this, we simply assume that at any point of its journey, wherever this mass is, let's say at some smaller distance, so the gravitational potential energy in that case is coming out to be negative g m over r. This is what gravitational potential energy is in terms of mathematical relation. If I give you a little idea at how we got to this equation, so I would simply say that work done by conservative force. Conservative force in this case is going to be gravitational force times some small displacement dx. So negative of g m over x square times dx, and integration of this from 0 to r will give us potential energy. So that expression which I wrote first, we got from this particular relation. So this came, as I told you, as an application of calculus. Without it, we cannot get it. But what
Mm-hmm.
we need is a relation, and we have this relation. So always remember whatever mass that small object is going to possess, whatever mass that planet or the big object is going to possess, and the distance between them. So negative of all those things will give us gravitational potential energy. Apart from this, we can also relate this relation in some other terms. So as I told you, suppose this is Earth and there is an object which is at certain height h.
Mm-hmm.
So whatever force is acting on it, which is acting downward, that force is something which is responsible for the work here. So if we try to calculate the work in this case, it is going to be force times displacement. Force acting here is mg and displacement is something which is h. The work done can also be written as mgh. I already told you about this, that this expression is something when we write, we'll write this expression when object is approaching the surface of Earth. What if object is going away from the surface of Earth? Then this work is going to be negative because the force and displacement which are actually acting and taking place on this object, they are in opposite direction. So we can say that object when it is going away from surface, work done is going to be negative. And always remember this negative sign has a lot of influence in these questions. So that is something which is about gravitational potential energy. And this is the points that you need to keep in mind. First, this relation, and another, these relation, because these are also gravitational potential energy, which is nothing but work done by the gravitational force or against the gravitational force. Let's talk about another type of potential energy, which is called spring potential energy. So we need to understand this fact that spring is something which always opposes external force acting on it. Like for example, suppose there was a spring, it's in its natural length, L I assume. So this is the natural length of spring. Now what happens here is suddenly someone applied some external force on the spring. As a result, spring stretches. It stretches in some way that there is some displacement in the spring, and that displacement can be represented by this X thing. But what is going on in the spring simultaneously? Spring will also apply a force in the opposite direction of this external force. And what we are actually observing here, that spring force, which is acting, it is acting in the opposite direction of displacement.
Mm-hmm.
What do I actually mean when I'm saying that it is actually acting in the opposite direction of displacement? Means because displacement is something which is a consequence of this external force, and spring force is not responsible for this displacement initially. The spring force is acting in the opposite direction, and because of that, the spring force is something which is directly proportional to negative of x. Or we can say that spring force here will increase as we witness more displacement against its natural direction. So when we remove this proportionality sign, we actually get a constant which is represented by k. This k is spring constant. It is a proportionality constant as well. Now, whatever value it may have, it is going to be different for different materials because of the characteristics of metals we use to make it. So that is the one thing we need to keep in our mind. This is the force which acts on the spring. So here we just assume that the moment it does some displacement x. So from its initial position, which can also be referred as mean position, we are able to displace it to one of the ends. And what we call these ends, we call them extreme position. The moment we release the force, what is the natural tendency of the spring? The natural tendency of the spring is to go to its natural length because of this spring force. But think and tell me once it reaches this position back, will this spring be able to stop?
Mm, no.
No. Why? Because once it reaches its mean position, now it must have some velocity.
Mhm.
And this velocity gives this mass some kinetic energy, and that kinetic energy which this mass possesses at this position will not let this spring stop at this point. So what will happen? The spring compresses this time, and that compression is also same as that of the expansion. And throughout this time when spring is compressing, because of this, spring force must be acting in the opposite direction of displacement once again. So that is the reason why we observe that spring force is something which is directly proportional to negative displacement, and this makes it reach its another position which is called extreme position. So once we set this system in motion, it will stay in motion if the experiment or this thing is taking place in vacuum. This will continue forever, and such motion are known as simple harmonic motion. You might learn about this in the upcoming units. Just try to remember that simple harmonic motion is something in which force is inversely proportional to x square. That is a different thing. I'll talk about it once we're studying this. So now the question is how much potential energy this spring will possess.
Mhm.
That potential energy is known as spring potential energy, and it is equals to half k x square, where this k is spring constant, its x is displacement from its mean position. So that is the only thing you need to keep in mind. And again, if I try to explain you that how we got this relation, so as I told you, potential energy is nothing but a negative of work done by conservative force. In this case, the conservative force is going to be spring force, which is negative of kx, and displacement is going to be dx. Once we solve this equation, we get this. Now we integrate this once again from 0 to x, and this will give us spring potential energy as half kx square.
Mm.
So this is how we got this by using the definition of potential energy only. So as there is no calculus, we don't need to discuss how this everything happened. Yeah, but the relation is important. We need to know the result.
Yeah.
Apart from this, there are few other things as well that we need to know here. Suppose this is the planet. This can be any planet. And from this planet, there is an object we can call satellite revolving around this planet in some of the possible ways. So now just tell me, first of all, how many types of satellite do we actually have? How many
Mm.
types of satellite do you know?
Types. I guess only the one that receives the waves and sends it back.
I'm talking about satellites.
Yeah, like the satellites that receive the like radio waves from the Earth and then it sends it back, right?
Then what happened due to it?
Mm.
Why we are doing this?
To like broad or like I guess send messages across the globe or broadcast stuff.
Okay, let's try to understand it. So satellites are basically of two types. You must have studied it. One is man-made satellites, others are natural satellite. So let's talk about, first of all, what satellite is. Satellite is something which revolves around a planet. So it revolves around one planet only in such a way that it complete one revolution in its specific time. Now, what does it mean? It means, like if we talk about moon, moon is our natural satellite. Why? Because it covers, or you can say it revolves around Earth in fixed number of days, which is 27.5 days. In every 27.5 days, moon completes one revolution around Earth. And that is the time for which we actually observe different phases of moon. So that is something which is natural satellite, revolving around Earth. Why it is revolving around Earth? That is also a question. It is revolving around Earth because anything which is revolving around a given planet, it shows that it is someday a part of that thing only. Like for example, we can say here this moon must be part of Earth some other day for sure. And as we all are revolving around Sun, all the other planets, this proves one thing again that someday we, or you can say all the planet, must be a part of Sun. And this is what different theories conclude as well. But physics also says the same because if anything is revolving around anything, it means that it was a part of that thing once upon a time. So, in order to let its gravitational force of attraction equally balance these two things, some planet do have different satellites. Jupiter has so many satellites, these are the natural satellites. Now, the one which is man-made satellite. So, man-made satellite has so many uses as well as so many types. So, the one thing which is very important, or one such type of satellite which is very important, is geostationary satellite. Every satellite has their different jobs. Then we have synchronous satellite, and then we do have some non-synchronous satellites. Each type of satellite plays a different role. What we need to understand here is the distance from the center of Earth at which this will revolve. It will depend upon one thing, and that one thing is that in how many days or months or years we want this thing, satellite, to complete one revolution. Based upon that only, satellite is launched and put into a orbit. That thing is called orbit, orbit of satellite. If we try to understand about these different type of satellite, let us just start with geostationary satellite. So as the name suggests, geographically, this thing must be stationary. What does it mean? It means that a point at which the satellite is, it remains at that point throughout the day. Or you can say it remains looking at that point as of, like, it has to be monitoring that part only. For example, different parliaments of different big countries do have satellite which always monitor their parliament throughout 24 hours. Surveillance is not only something which stays what we see, it is also something which we can't see. So they used to track off each and everything using each and everything possible. So that is something, that satellite is something, it's called geostationary satellite, whose job is to look at just one particular place. And obviously that particular thing should be very important. So most of the countries has those kind of satellites to see their, you can say, parliaments. Apart from this, and one important thing that you need to keep in mind, a geostationary satellite in general revolves around 36,000 kilometers away from the surface of Earth. Like the satellite is revolving that much kilometers away from the surface of Earth. It's a big thing and keeping everything intact. So there are so many other things. What are the uses of geostationary satellite? Different companies also uses geostationary satellite to increase their signal transmission thing. Satellites, as you told, it is used to reflect signals. By using satellites, we can spread signals like almost everywhere. And Starlink is also working upon one of these things. It wanted to give Wi-Fi directly from space. And if that thing came into existence as soon as possible, I guess it will be there. It will again revolutionize so many things. Like we will expect network at those areas where there is no, you can say, possibility of getting it earlier on, but we will have it soon. So that is one such thing. Are you getting all this?
Yeah.
Apart from this, we have another two major satellites. These are the categories which are decided by, you can say, the world. These are the ranges basically. In a one particular range, these kind of satellites can do their job, and another range, another type of satellite can do their job. Some satellites do revolve very close to the space of surface of Earth, so those satellites can be regarded as orbital satellites. It are just orbiting. Then we do have polar satellites as well. Those revolves around the polar orbits. That is also the case. Apart from this, we can talk about another important aspect, which is called energy of a satellite. How much energy a satellite can actually possess. So we will try to find out the total energy, and that total energy is going to be kinetic energy plus potential energy. So just try to understand the concept. Whenever you are solving numerical, you'll be easily able to solve it if you know the concept. Again, we'll imagine that there is a planet, and around this planet there is a satellite revolving in this orbit. Now you can clearly see the satellite is at certain distance from the center of the planet. You can call this distance as r. Apart from this, it must be having some velocity, and that velocity, obviously, it is going to be tangential. So if you just try to understand this fact that due to rotation, or you can say due to tangential velocity, satellite must possess one thing. What is that?
Mm.
Kinetic energy. If anything is moving with certain velocity, it must means that it must have kinetic energy. Apart from this, due to this position from the center, or due to this position with respect to the center, satellite must possess potential energy as well. So both of them will be contributing towards the total energy of satellite. What I want you to remember is we already saw in this class only that potential energy and that to gravitational potential energy is nothing but Gmm over R. Similar to this, we need to also understand that apart from half mv square, the kinetic energy can also be Gmm over 2R. So these are the two relations that you need to remember. Potential energy is always negative of Gmm over R, and kinetic energy, apart from half mv square, it can also be written as Gmm over 2R. And this is the kinetic energy of satellite only. So basically, we got this through that only. Velocity is something which can be easily found out using equations only. But Gmm by 2R is something you need to remember. So if we try to find out the total energy comes out Gmm over 2R minus Gmm over R. Once you solve this, we will be having negative of Gmm over 2R. So total energy is something which is less than that of potential energy. This is the most unacceptable thing when we were just done with mechanics. Because
Mhm.
ideally, if you just look at these two relations, potential energy is twice of kinetic energy. This is the most important part here. We'll be solving some numericals directly based upon this. And if we try to relate potential energy and kinetic energy, we can say that kinetic energy is something which is negative of potential energy over 2. Or you can say negative of half of potential energy. Similarly, if we talk about the relation between kinetic energy and total energy, what it is going to be, we can simply say total energy is equals to negative of kinetic energy. So whatever kinetic energy the satellite possesses, negative of it is going to be total energy. So these are the three relations between these three forms of energy. So that is also something you need to keep in mind. Does this make sense?
Yeah.
Now let us try to understand the forces acting on these satellite in order to get the velocity of it. Like what is the velocity of it? We need to calculate it. Let us try to understand that how we can calculate the velocity of orbiting satellite. And that velocity is known as orbital velocity. We'll also see a relation. We'll also find the orbital velocity of different satellites on Earth. Again, this is going to be the general case because we assume that all the satellites must be revolving close to the surface of Earth. So, in order to calculate the velocity, we need to assume again this is our Earth, and there is a satellite revolving at this point, our distance away from the center of Earth, and going with velocity. And you can assume it is revolving in this way. Let us try to understand what are the forces acting here. So, one force which is acting on the satellite due to the mass of Earth is going to be gravitational force. Apart from this, as it is going in a circular motion, there must be some centrifugal force, or you can say centrifugal force acting outwards. As these two forces must be balanced, or this thing can only rotate if these forces are balanced. If these are not balanced, it must not rotate. And we do see that satellite do rotate. So what we actually did at that point, we try to balance out these two forces. So if Fg is equals to Fc, then only this is possible. Or you can say then only such motion is possible. So here we know that the gravitational force is nothing but Gmn over r square, and this centrifugal force is nothing but mv square over r. If we try to solve this, we'll get velocity as root gm over r. And when we put all the values into this relation related to Earth, when we substitute these values in this relation, like which one? G is nothing but 6.67 times 10 to the power minus 11 Newton meter square per kilogram square. Again, we need to remember the unit. Mass of Earth, it is 6 times 10 to the power 24 kg. This is the rough estimated value. If it is there in the question, we will use that thing only. If it is not there in the question, we'll use this particular value. Apart from this, if you try to consider that the satellite is revolving like very close to Earth's surface, such that r is radius of Earth only. So in that case, radius of Earth is taken as 6,400 kilometers, or you can also remember it as 6.4 times 10 to the power 7 meters. So if we substitute all these values into the relation, the orbital velocity we are going to obtain after substituting all these values, it is coming out to be 7.8 kilometers per second. That's a huge number. To be precise, 7.92 kilometers per second. So that's a huge number. So if a satellite wants to revolve even close to the surface of Earth, its velocity needs to be minimum 7.92 kilometers per second. And this is called orbital velocity. And that is the velocity when, like, this height in comparison to the radius is very less. Then only we can take r as radius of Earth only. Like this r is re plus h.
Mhm.
So that is one such thing. And these were the few things that we need to know before actually going into that assignment part.
Got it.